All right, so quick review from what we had last time. We sort of started this chapter, and we introduced the zeroth law and the first law of thermodynamics. The zeroth law talks about thermal equilibrium. Right? If object A is in thermal equilibrium with object B, and object A is also in thermal equilibrium with object C, then B and C must be in thermal equilibrium with each other. Why do we need that? Because that tells us we can take something's temperature. A thermometer can be in thermal equilibrium with some object, and we mark on it what the temperature is. And then when we put the thermometer in thermal equilibrium with another object and it goes to the same line, we know it's the same temperature. So it just tells us that we can take something's temperature. The zeroth law of thermodynamics tells us we can take something's temperature. The first law is conservation of energy. So this is about, we've got some system, and we want to know how the energy of the system changes, the internal energy of the system. Well, what does it depend on? It depends on what we put in terms of heat and what we put in terms of work. If we add heat, then the internal energy goes up. If we do work on the system, the internal energy goes up. The reason there's a negative sign here is because this would be the work done by the system, the work done by the gas. So if the system does work, it's going to lose some of its energy, right? It's giving it up to whatever it's doing work on. We'll be using this a lot, and we'll have a worksheet today that will go over the help you come to grips with this equation. First law of thermodynamics. So in the upper image, you can see that there's a piston here. I think that one worked out okay on the photocopier. But down here, it's a little hard to see. There's a piston. The position is a little lower on the left side and a little higher on the right side. You got that okay? Same over here. There's a piston here. And then on the back page, they're at the same height. Okay? So what you want to do, maybe we can read through part of this together. And then work through it and compare answers with your neighbor. And then we'll sort of get together periodically, make sure we're all on the same page, make sure we all have the same answers, and then we'll move forward. But we're starting out with this system, and we're going to use this a lot. A container with a movable piston as the lid. It's sealed so that the amount of gas inside the cylinder remains constant, and it is frictionless. It can move freely up and down, and that's our system. So there it tells us the cylinder contains an ideal gas at room temperature. It's sealed with the piston of mass M, cross-sectional area A, free to move up and down without friction. No gas can enter or leave the cylinder. The piston is at rest. Atmospheric pressure is pushing down on it from the outside. So they want you to draw a nice free body diagram for the piston. And then you can work your way through the first few questions, and then we'll come together and talk about them. So the first thing we're doing is drawing a free body diagram. What's one of the forces acting on our piston? The what? The weight of gravity. So I'll put on the piston due to the earth. Use the subscripts there. Anything else?
Pressure.
Pressure.
Going upward.
pressure. I'm listing forces here, right? So this is the force on the piston from what? The gas inside? What else? Anything else acting on the piston?
Downward force, pressure, atmosphere.
On the piston from, I think we're calling it P sub 0, right? We good with that? Anything else? Everyone has three forces acting on the piston? Okay, part B. That is part B. Part C. Oh no, part B. What's the net force? Net force acting on our piston. Is it, what direction is it?
Wouldn't it depend? We don't really have any values.
What do we know, though? It's not moving.
Okay, so it should be 0.
So it's 0, right? Because it tells us, what does it tell us? The piston is at rest. It tells us it's free to move up and down, but it's at rest. So that means that the net force has to be 0 on it. Is the force exerted on the piston by the gas inside the cylinder greater than, less than, or equal to the force exerted on the piston by the gas outside the cylinder? More, because it's not only holding up, it's greater because not only is it holding up the force from the gas outside, from atmospheric pressure, it's also holding up the weight of the cylinder. You see that? And what's our equation that puts all this together? Sum of the forces has to be 0, right? So we get the force is a vector equation. So some of these will be in the positive direction and some will be in the negative direction. But we know that they sum to 0. Okay? Nice little review of chapter 4. All right, let's keep going. Is the pressure of the gas inside the cylinder greater than, less than, or equal to atmospheric pressure? Because we just said the force was greater in part C, and the areas are the same. Pressure is force over area, so the pressure is going to be the same. Sorry, pressure is going to be the same answer as the force. So the force of the gas inside is greater than the force from the gas outside. The pressure is greater inside. And we can use our previous equation to figure out what it is, right? Force is pressure times area. And I just use the previous equation and solve for the pressure of the gas. Okay, we ready to move on? E. A second cylinder contains a different sample of an ideal gas at room temperature. The two cylinders and their pistons are identical. The original one, the location is a little bit lower. The second one, the piston is at rest at a higher location. They want to know how the pressures of the gas inside those cylinders compares. So talk it over with your classmates for a second, and then we'll discuss it. Anybody get it's greater than? The whole table, or just you? They couldn't convince you? You couldn't convince them?
How is it greater if the area is larger?
What's it? The area?
So the area is larger. How is it that the pressure is greater?
Well, which area is what's important? We're looking at the force really on the piston, right? So it's the area, the cross-sectional area of the bottom of the piston that's important. And that's the same in both cases because it's the same cylinder.
Oh,
You see that? You're right, the surface area of what the gas is touching increased when the piston went up. But what we really care about is what the gas that's touching the piston.
so it's the surface area of the piston that
Yes.
matters. Okay.
What else? Same? Less? But you guys are undecided? Less? Less? Okay, so what's the thought? You thought about the area going up? Is that what you thought too? So a couple of you about the area. And then more because it's higher up, something had to push it up. And why the same?
Between the two cylinders, the pressure due to weight isn't changing, and pressure of the atmosphere on this isn't changing, so therefore the pressure in the cylinder must be the same.
What do you think? Just sort of what we did with this other cylinder, right? We said those are the forces acting on the cylinder. We've got a weight down, and we've got a force down due to the atmospheric pressure outside. And so the gas has to push up with an equal force. Add those two together, and that's what the force has to be up because the piston's not moving. And that's what we said in the part A, right? Now, we've got two different cylinders. The weight of the piston, same for both. The force due to the atmospheric pressure, same for both. Is the piston moving in either case? No. So the upward force has to be equal to the sum of the two downward forces because the net force on that piston has to be 0. So they both have to have the same pressure because the area is the same. You see that? It's because it's the force. What we care about is the force on the piston. So we care about the cross-sectional area of the piston. It doesn't really matter that there's more surface area inside. Okay. Next page says, we're taking the same type of cylinder with a fixed amount of gas in there, and we're going to start it out by putting it in an ice water bath, letting it come to equilibrium. And we're going to call that P initial, V initial, T initial. Then we're going to pull it out of the ice water bath and stick it into boiling water and let it come to equilibrium. And we'll call that P final, V final, and T final. So the initial condition, everything's in the ice water bath. and it's at thermal equilibrium, it's been there for a while. The final condition, it's in boiling water, it's in thermal equilibrium, it's been there for a while. So go ahead and compare the initial to the final for the temperature, the pressure, and the volume. They started you off with the easy one. What happens to the temperature?
Increase it.
Right? Starts off in ice water, ends up in boiling water, temperature goes up. Okay. Are we ready to move on? Pressure. How do the pressures compare, final to initial?
I thought it was greater too, because once you increase the temperature, it's gonna result in excited molecule, or it's gonna raise the pressure, but I'm not sure whether the piston is moving or not.
It's the same type of cylinder we had in the previous case. So the piston is free to move up and down on a frictionless surface there. Did you understand that? So if you did not allow the piston to move, right, if the volume was fixed and you heated it up, the pressure would increase also, right? I think we all agree with that. In this case, the piston's free to move. You heat up the gas, what's going to happen? Piston's going to move up. Do we agree with that? So we can answer number 3. And eventually it's going to stop moving up. And it's going to be in equilibrium. So what sign should I put in here? P final is equal to P initial. Because what we end up with is the same as what we had the previous question, right? One cylinder with the low piston, one cylinder with the high piston. The one with the low piston, that's what this gas is like when it's in the ice bath. Then you put it into the boiling water, and now it looks like the piston on the right with the higher location. But the pressure is the same in both because the weight of the piston has not changed, and it's in equilibrium, it's not moving, and atmospheric pressure has not changed, so the internal pressure has to be the same. This is a way of keeping the pressure constant. A vessel like this, with the piston that's free to move, is a technique for keeping the pressure constant inside as you take the gas from one state to another. Okay, so this is consistent with the previous exercise. And it says, is it consistent with the ideal gas law?